Of course. Development in historical astrometric visualizations, a tool for plotting multi-star systems.
All right, I'm just going to start sharing my screen soon. All right, everyone can see that okay? Perfect. Okay, so hi, my name's Andy, and I'm excited to present my tool for plotting historical positional data of multi-star systems today. So 2 years ago, I enrolled in a course called Double Stars. This is offered by a nonprofit organization called Voice Research Initiatives and Education Foundation, otherwise known as BRIEF. And this course aims to introduce students into astrometric research and the analysis of double stars, with the goal of publishing a paper in the Journal of Double Star Observations. And so before we dive too deep, let's clarify a couple of terms. A double star is known as two or more stars that appear close to each other in the sky. These can either be gravitationally bound or not gravitationally bound. And then when we don't know, we call these doubles uncertain. We have components in pairs. So individual stars in the system are components, and they are typically labeled in alphabetical order from greatest brightness to least. Pairs are the relationships between any two components in a system. And in order to take measurements on a multi-star system, we have to measure the position angle and separation between the components or the pairs. And so the Washington Double Stars catalog is the most comprehensive catalog of double stars in the world. It's maintained by the United States Naval Observatory, and this catalog includes a wide range of historical data, such as observation epochs, position angles, separations, magnitudes, and so much more. It really is a rich source of data, and this tool takes advantage of the data supplied by this catalog. So for the tool, I did use Google Colab, which is a cloud-based platform that lets users write and execute Python code within their browser. And this environment is especially useful for education because it's not specific to one operating system, and it allows for a deep level of annotation and description of the functions of the program. So going back to my project, I chose an uncertain triple star system as pictured here. This system has 3 components and 3 pairs, and I didn't know if any of them were gravitationally bound or not. And so my team was tasked with assessing whether or not this system was a physical triple star system, and we wanted to publish our results in the JDSO. Now, this can all be solved using various statistical methods, but the challenge actually arose when trying to plot the system's historical data. And I was surprised to see that there was no automated way to obtain the necessary plots for a multi-star system. And I noticed that other students who ran into the same issue would use Python to create plots for their projects. Others would create spreadsheets, and the solutions for this problem were applied case by case. And I wanted to create something that was a little bit more versatile. So I decided to create a program that could handle any WDS file for any system and produce a publication-ready plot. So here's an example of a WDS file that one would receive from a data request. So the top section, we have the historical AB measurements. And in the bottom section, we have historical AC measurements. And really, we only need 3 columns out of this whole file. First, we have the epoch or observation date. Second, we have the theta or position angle. And finally, we have the row or the separation of the pair. And the tool filters out this unnecessary data and converts polar coordinates to Cartesian coordinates, integrates student measurements into the plot if they've provided that, and they can easily include this plot in their research papers. So this is the output of the program given the previous WDS file. There are two types of plots in this output. We have the top center one, which is the overall plot, and that just gives a general overview of the system with the primary component at the origin. And then we have two zoomed in plots for each of the other pairs, and just to show the drift of the position over time. And we can also see at the black X on each of those plots shows the user's own measurements. So that's actually my team's measurements from that. And then as we can see, it's also color coded. So it goes from blue to red to indicate the passage of time. And so here's actually the performance of the septuple star system as well. And we can see that with ease, this plot will produce beautiful visualizations of the positional drift of double stars over time, no matter how many components it holds. And I actually wanted to run through the plot tool with you guys in real time, just to show you guys some added functionalities. Everyone can see that okay? So we have the plot tool right here. First off, I just want to point out that there's an outline on the side and navigate to different parts of the program easily. And also I want to go and show when you go into the folder of the drive, I have added a figures and a resources folder. This resources folder is important because it holds the necessary files for completing the program. And so if we go in there, we can see different measurement files and also the WDS files. We also have a figures folder, which is empty right now, but when we run it, it's going to fill up with our figures. So let's go to the top of the file. And I have a couple of example ones here, but I'm just going to run this bottom one. So we just go ahead and run all, and it's going to run through the program. And if you want, you can mosey your way down. You can read every single line of code if you want. And I tried to annotate as much as I could to give understanding to anyone who is reading it. And you can see the evolution of the text file as it turns into a data frame, and the data frame turns into a visualization. And so we have the overall plot right here, and then we have the, and then we have the zoomed in plot right here, as well as the student's measurement, and then the passage of time. And so if we go back to that figures folder, we can see that the plots are actually going to be added. And then, of course, we have some PNGs that we can add into our research papers and then submit that to the JDSO for publication. So back here. So finally, using a notebook has so many benefits to student learning. First of all, many students I encountered only had access to a Mac or a Linux operating system, and to use this tool, all they need is an internet connection and a Google account, and this makes research more accessible. Second, the nature of using Jupyter Notebooks makes coding easier to understand and easier to engage with, and students can play around with the code that they want. There's no secrets. You can see every single line of code that I put in there, and I really encourage people to manipulate it in the ways that they want and the ways that work for them. And then third, we're simplifying multiple steps of the research process. With an automated plotting tool, students can breeze through this section of the research. And then knowing that it's within the JDSO guidelines, reviewers will actually spend less time correcting plots and then having that back and forth. So yes, I would love to give a special thanks to Pat Boyce, who's been my mentor for the past 2 years. And he has given me so much encouragement and so much guidance, and I wouldn't be here to have presented this to you all today if it weren't for him. And I would also like to thank the United States Naval Observatory for maintaining such an extensive database that we all benefit from. And finally, thank you all for listening to my presentation today.